Okay, so now that we've identified some of the basic properties of the three particles, the alpha, beta, and the gamma, let's take a look at the way that these particles are organized by looking at a new type of representation called the Segre plots. So in the last chapter we discovered that there were variations of elements that we refer to as isotopes. And the isotopes, differences between isotopes I should say, is the number of neutrons that they have. Of course an element is defined based on the number of protons that it has, but there are many variations with different numbers of neutrons. So far we know that there are at least 2,500 possible nuclides, and a nuclide is a unique combination of protons and neutrons. And of those, only about 300 of them are stable. So that means that the rest of them undergo radioactive decay or eventually break down into smaller parts until eventually they reach one of these 300, at which point they become stable. So the idea of the Segre plot is that we give each nuclide a separate box, whereas the periodic table only gives each element its own separate box. So this representation will look something like this. And of course this would continue on. Down here we're looking at the proton number, and of course this would be the Z number. Around the vertical axis we're going to look at the neutron number, not the A number. The A number is the atomic mass or the combinations of protons and neutrons. We're not going to look at that number. Instead we're going to look at the number of neutrons that each particular atom has. So over here this is the neutron number, and that is, use the letter N to represent that. So with no protons or neutrons, of course no atoms have that particular combination, but in the bottom one down here we have hydrogen. And then hydrogen has several variations. There's hydrogen with no neutrons. There's also a version of hydrogen with one proton and one neutron, and a version of hydrogen with one proton and two neutrons. And then beyond that we don't see any combinations of this particular number of protons cannot have three neutrons. When we move over to two protons, we find that there are no variations of nuclides with two protons and no neutrons. But we find that if we add just one neutron, so we have a total of three particles, then we can make a form of helium which has an atomic mass of 3. 2 protons, 1 neutron for a total of 3. The most common form is 2 protons, 2 neutrons, and of course, to remind you, this one right here is the alpha particle. Alpha particle has 2 protons and 2 neutrons. There's also a variation of helium that has, of course, 2 protons and 3 neutrons for a total mass of 5. So as we continue on down the chart, find that the next one comes here, and this guy is lithium. And lithium has several variations. The next one after that is beryllium. And beryllium has quite a few combinations. So typically the periodic table would have taken the average based on the number of these different variations that exist in nature and come up with an average mass and simply put that down for the mass. Where the Segre plot actually gives every single individual, just to remind you, 2,500 of these nuclides. So as you can imagine, this table is quite large as we get up to the larger atomic nuclei that have more protons, I should say, and then many, many more combinations. The smaller ones tend to only have 3 to maybe 5 different nuclides, but as we get up to the heavier atoms like iron, lead, uranium, find that they may have as many as 20 or 30 potential nuclides. So they may fill a large section or a large column with many variations of isotopes. So this is sort of the close-up view. But if we look at the Segre plot in a little more broad terms, find that the highest number goes up to about 90, and similarly we'll go up to about 150. So proton number, the Z, this is the neutron number. N, and if we could imagine the line that would represent the path where we have exactly the same number of protons and neutrons, that line would look something like a 45-degree angle. And we would call this the N equals Z line. You'll notice that if you look back in the close-up version of the chart that we find very commonly combinations of 2 and 2. For lithium we find 3 and 3. For beryllium we find 4 and 4. You find very commonly at these points where you have equal numbers of protons and neutrons. So in the early portion of the chart, it basically tends to follow that N equals Z line until we reach approximately number 20. And at number 20, the Segre plot tends to start to broaden a little bit, gets a little wider, and it also starts to leave that line and curve upward. And the significance of this is that we are having more neutrons than we have protons. So looking at a large scale picture of the Segre plot, you can see that there's sort of this region of the periodic table around atomic number 19 or 20 where it's now requiring that we have more neutrons than protons to create that stability that we need in the atom. And we're going to talk more about the Segre plot and the significance of this deviance from the N equals Z line in the future.